All right, so let me quickly go through the idea of the coefficient of correlation, R, and how to use the table of critical values of R. The idea of R is it measures how close your scatter plot is to a straight line. For example, if you have your scatter plot with all the dots perfectly on a straight line, then that's the perfectly positive correlated set of points, and it has R value of +1. And now on the other hand, if you have your points perfectly aligned in a negative slope, then it is perfectly negatively correlated and it has R of -1. The highest value of R is +1. The lowest value of R is -1, and they're both perfect. One is perfectly positive and the other is perfectly negative. And then if you have a set of points that are nothing like a line, then you have no linear correlation at all, and your R is equal to 0. So if you're looking for linear correlation, then you want either +1 or -1 or near there, but you don't want 0. 0 is not what you're looking for. Now, most things in life are not perfect. You could have a scatter plot that's pretty good, pretty much like a straight line, but not perfectly good. Then this R is almost 1. Or you could have a scatter plot that looks like a straight line, but it looks like a straight line with a negative slope. So it has a coefficient of linear correlation R of almost -1. So having +1 is really good. Having -1 is also really good. But if you cannot have that, then you take something that's almost +1 or almost -1. What you don't want is something 0. Something near 1 or -1 is good. Something near 0 is not good if you're looking for linear correlation. How close to 1 is good? How close to -1 is good? Well, let's look at the whole layout. Let's look at the whole number line of R. R can be as low as -1 or as high as +1. Anything that's near +1 or near -1 is good, and everything that's near 0 is no good. So there's a cutoff that people calculated called the critical value of R that tells you that if you are closer to 1 than the critical value, or over here on the negative side of it, if you're closer to -1 from the critical value, then we conclude that there is linear correlation. If it's in between plus or minus critical value, then we conclude that there's no linear correlation. So what happens if we look up the table of critical values? The table of critical value has 2 columns. One column has the sample size, how many XY pairs do you have? And the other column is the critical value. Then, for example, if you have 10 pairs of XY numbers, and then your point is either more than 0.632 up to 1, or less than -0.632 down to -1, then we conclude that there is linear correlation. But if your R is somewhere in between the critical values, positive and negative critical value, then we conclude that there's no linear correlation. You will notice that the critical values of R decrease as the sample size goes up. The more pairs of numbers you have, the less you require of R. This is a very short table. It only goes to 14. But even the long tables only go to 100. So if you have an n that goes over whatever the maximum of the table is, then if it beats the number for 14, if it beats 0.532, either positive 0.532 or negative 0.532, then it's good. For example, if your sample size is 25, but the table only goes to 14, you know that this critical value over here will be less than 0.532. If your R turns out to be, let's say, 0.61, then 0.61 is more than 0.532, and your critical value with n equals 25 will be less than 0.532. So you also know that you have linear correlation. So sometimes you don't need the whole table. Now, of course, if it comes out less than 0.532, then you don't know there. Another way of saying it is that if the absolute value of R is greater than your critical value, because absolute value goes both ways, positive and negative, then the rule is that if the absolute value of R is greater than the critical value, then there is linear correlation. And vice versa, if absolute value of R is less than the critical value, then there's no linear correlation. Hope that helps. Thanks for watching. Bye.